Hey guys, can you hear me? Can you see my slides? You can type in the chat window to let me know. Thank you, Thomas. All right, let's get started. So first, I want to go through a set of slides, not very long, to introduce the basic phenomena, and then we'll start playing with CLT code and do some virtual experiments. Okay, that's the plan for today. All right. So I want to talk about the deformation coupling phenomena in composite materials. This doesn't exist in isotropic material like metals or alloys. These are unique features of composite material. All right, most of the material are from Bob Jones' book. If you're interested, you can read through it. Mechanical composite material. So composite material is really many layers bonded together, and there is a good reason why bonding them together. Why don't we keep them loosely stacked up without bonding? If you don't bind them together, there is no bending stiffness. The bending stiffness is very, very low until you bind them together. Once you bind them together, they will actually strongly coupled, meaning that they will interact. That's the fundamental nature of the coupling phenomena, because a different layer have a different characteristics, and they want to go different directions under load. Sometimes that create interesting phenomena. Okay. Now this is an example of basically demonstrating, this example right here, demonstrating what is the stiffness of two layers if you loosely attach them together, just stack them up, the bending stiffness as reflected by the deflection under a fixed load P is this number right here. If you glue them together or nail them together, it's much higher. That means deformation much less. In this case, it's a quarter of deformation if compared to the when you keep them loose. So that's the very good example. These are based on beam theory. You can prove them with what you learn in solids. Very good example. All right, so the laminate that we have learned, basically assume all the layers are tightly bonded together. They're bonded together. They stay together. The interface not separable. Okay, unless you overload it, unless you go over the failure threshold, they debond and things like that. But before that happens, every layer are close coupled together. They don't separate. They're one piece. Okay, and their phenomena are captured by this set equation that we learned before. So basically, how does a laminate respond to a external effect? The force, which is the N's are the force, normal force and shear force. M's are bending and twisting moment. How is laminate respond is captured by this. This is a linear relationship. This is the first order dependence. Very powerful theory. It indeed can predict a lot of phenomena. ABD are calculated based on your layup as well as the thickness distribution, right? We learned all these. We've done it many times. Now I want to talk about the physical significance of A, B, and D. What is the physical significances of A, B, and D? What is the so here are the answers. We'll learn them in a deeper sort of way by doing experiment later. But I just wanted to basically go through the standard answers now. So A1 6 is some textbooks use 6 instead of 3. The reason is because the tau xy is considered epsilon 6. There are 6 string components. In-plane components are epsilon x, epsilon y, and gamma xy. Gamma xy is frequently considered epsilon 6. So that's why 6, and they use 6, this means 3. So in the 6 is here. This is a 6. You can call it 3, it doesn't matter. So it's just a matter of name. Okay. A16 and A26, these two numbers are all these matrices here, A, B, and D are symmetric. If you you can prove that easily using these equations here. They're symmetric. Q is symmetric, so basically A is symmetric, B is symmetric. No matter how do you sum and add and everything, a symmetric matrix add a symmetric matrix remains to be a symmetric matrix. So A, B, and D are all symmetric matrices. Okay. So A16, A26 are the extension shear coupling terms. That's a term when you have, if you pull the material, it might have produce a shear, or if you shear the material, it might produce a tension, extension. So those are the terms. A16, A26 are the in-plane extension and shear coupling. Okay. When those terms are zero, that means there is no in-plane shear extension coupling. If you shear the material, it just shear. There's no extension, there's just gamma. Vice versa. Okay. So that's the significance of A16, A26 here. And the B matrix, the entire B matrix is the bending and extension coupling terms. All of them, the entire B matrix basically relates, see the B matrix multiplied curvature adds to the extension load. In this case, the B matrix multiplied by the extension strain give you the bending moment. So these terms, B matrices, is basically capture the interaction between in-plane extension and out-of-plane bending and twisting. So that's the coupling term for that. And the D matrix, the two term in D matrix, D16, D26, these two terms, 16, 26, are the bend twist coupling terms. Kappa XY is the twisting. Kappa X and kappa Y are the bending curvature. Okay, there are two directions, X and Y. The curvature in the X direction, curvature in Y direction. That's kappa X and kappa Y. Kappa XY is the twist. So D16, D26 basically represent the interaction of these two modes. All right, so in a graphical form, this is the coupling terms. All right, so in the example problem, I asked you to do several examples of different layups, and some are symmetric, some are quasi-isotropic, things like that. What I'm looking for is you should, if you do it correctly, you should have these terms to be zero if you for certain layups. We'll go through that case by case. Okay. All right. So graphically, this is tension twist coupling. When you have tension, there's a twist. This is a graphical representation of that. What it looks like. That means if you just apply pure tensile load in certain directions, the material will stretch longer. Not only stretch longer, it actually rotate a little bit. It tends to rotate. If you don't constrain the rotation, it'll rotate, naturally rotate a little bit. That's tension twist coupling. And this is a bend twist coupling. If you have laminate, you put a bending moment on it. Okay. Without bending twist coupling, it just bends. See, it just produce a curvature associated with the bending moment, right? If your material has certain coupling terms, when you bend it, it actually tends to twist. The twist is more pronounced if you look from the side. If you look from the side, the end twist. As you bend them, the end twist. The more you bend, the more you twist. Okay. This is a bend twist. This is a twisting caused by bending. Usually these things are reciprocal. If you twist it, it also bend. Okay. All right. Any questions so far? All right. Let's start with looking at the simplest case. The simplest case is the isotropic layer. Single layer of material, which is isotropic, which essentially result in the B matrix. Entire B matrix is zero. There are no B matrix. Okay. If you do isotropic material as an input, no B matrix, and then A matrix look like this, D matrix look like this. What you can see is for isotropic material, all the coupling terms that we see here. All the grade ones are 0. All the ones in gray are 0 for isotropic material. So the other way you can say it is isotropic material is free of any coupling phenomena. There's no tension shear coupling. There is no extension bend coupling. There's no bend twist coupling. None. No coupling. Okay. That's isotropic material. All right. Now there is another class of material which is called a quasi-isotropic. The quasi-isotropic material is some special layup. What happens when you do this layup? The extension matrix, the A matrix, looks exactly like this A matrix in isotropic material. So basically, for that layup, what you have is your A16, A26 term is 0. These are example of quasi-isotropic material. This is one, and this is one, and this is another one. This is also quasi-isotropic material, quasi-isotropic material. Okay. And then B and D matrix are not really can be any form. So so quasi-isotropic is only isotropic in the sense of the A matrix of that quasi-isotropic laminate represent is the same as a quasi-isotropic material in this case. So they only apply to A matrix. Okay, that's quasi-isotropic. And then there's a symmetric laminate. The symmetric laminate is a laminate with the symmetry at the midplane. So if you have a layup, you have a midplane, you find a layer above the midplane somewhere with certain directions, certain material properties, and then at the symmetric location beneath the symmetric plane, there is the exact same orientation, same layer, same material. So basically, there's a symmetry in terms of material stiffness as well as orientation with respect to the midplane. That's a symmetric plane, symmetric laminate. Now you can prove for symmetric laminate, the B terms are all 0. And the A term and D term, there's no patterns. They could be anything. So, okay. So symmetric laminate B is theoretically 0. It's all 0. So that means for symmetric laminate, there is no bending extension coupling. Okay. That's a symmetric. In most applications, in most designs, people like to use symmetric layup. Now, if you use unsymmetric layup, the chance of a bowing is pretty high because when you have the material cured in a manufacturing setup, and then when you have you cool it down, you will have thermal load. If the material is not symmetric, there is the extension, bending coupling, your parts will tend to bow just like this. All right, it's not surprising because the material actually can expand a lot. It's a matrix material, has huge thermal expansion coefficient. So if you use a unsymmetric layup, you want to make a flat plate. You put it on a autoclave and cure. Once you take it out after curing, it's not a flat plate. It's a cylindrical plate. Okay. If the plate has a symmetric layup, these are less likely to occur. It's more likely to remain flat. Okay. Why I say unlikely, not absolute term, because the sometimes the temperature gradient, not only the symmetry contribute to bowing, sometimes the temperature gradient also affect curing. So you might have a differential thermal convention, even though you're a symmetric layup, you could still have bowing. So use symmetric layup does not rule out bowing. It just makes it less likely to occur. Okay. If you use unsymmetric laminate, is very likely to occur. Okay. Any question, comments? All right. Now, balanced laminate. What is balanced laminate? Balanced laminate is a laminate for every theta lamina. There is a minus theta lamina of the same thickness stiffness somewhere else. It doesn't matter whether you put in a symmetry position or not symmetry position. It just it's almost like the lamina come in theta minus theta pairs. So that's a balanced laminate. For balanced laminate, you can prove that Bij is also 0. So there are no band extension coupling. Okay. So balanced laminates are also less likely to bow. Balanced. Okay. There is anti-symmetric laminate. Anti-symmetric laminate is the opposite to symmetric laminate. So basically, when you have plus theta above the midplane, at the symmetry location below the midplane, there's minus theta. So it's the opposite. So if all the lamina are arranged this way, obviously you need an even number. You need an even number of lamina to make purely anti-symmetric laminates. So for every theta above the midplane, there's minus theta below the midplane at the symmetry location. That's anti-symmetric laminate. For anti-symmetric laminate, there is pronounced band extension coupling. Okay. So that's the worst for warping and deformation after curing. That's the worst you can have if you're anti-symmetric laminate. Sometimes is it desirable for certain things to keep in a twisted form, in a sort of a warped form. Sometimes that's desirable, but most cases that's not desirable. Okay. But the interesting thing is, when you make anti-symmetric laminate, you have a strong band extension coupling, but you do not have a shear extension coupling. You do not have band twist coupling. You can mathematically prove that. That's term always 0 if you have strict anti-symmetric laminates. Okay. And we have most of these coupling are desired are considered as a bad effect. You have to deal with. It's not like when you take a piece out of the mold, a certain shape is once you take out of the mold, is other shape is considered a bad thing. There is this positive application, which is very famous, is for aeroelastic tailoring of the wings for this experimental airplane. There's one produced by United States called X-29. I think there's another version produced by Soviet Union, former Soviet Union, similar configuration for experiments. It's so-called forward swept wing jets. So this kind of jets has an inherent unstable wing configuration. The unstable in the sense that if you fly this jet fast enough, the wing will basically tear itself out. It will tear itself apart due to the fact that there is instability. So if you sweep the wing forward, when the aerodynamic load try to bend the wing also twists a little bit. The twisting is in the sense that the aerodynamic load will be higher, then therefore you bend a little bit more because of twist. Then you twist a little more, and then you bend a little more. So that cycle, when the wing actually widely vibrate and flip back and forth until it twists off. That's called a aerodynamic instability. The wing is not stable. You cannot fly this thing very fast. The only thing you can make this work is you make sure your wing doesn't even twist. It's very stiff, a very little bend. So you need to put a lot of mass, put a lot of weight to make the wing stiff. And that usually weight is against any aircraft design. You don't want any craft to be heavy. If you make the wing flimsy, you will have this bad aerodynamic instability, aeroelastic instability. So it looks like there's no path forward until people find the composite material. You can actually tailor the composite material. When the wing bends upwards, the wing will also twist in the sense that it will reduce the angle attack. Okay. You can manipulate the band twist coupling term D16, D26 by playing with layup. So it bends, when it bends, it twists in a way that angle attack is less. So indeed, these airplanes, experimental airplane built that way. They're very flimsy wings. They're thin foils with very flexible wings. They had the correct coupling terms. They are actually inherently stable. They don't show the instability. So that's enabling the composite. The coupling phenomena is what enables the forward swept wings. You cannot do this with metals. Okay. All right, so that's pretty much the story I want to tell. And then I want everyone to fire up your CLT code. Let's play with the code and let's check these couplings. I'm gonna start with my code. Let's first set up some common inputs that we use. Let me put a slide here so you can see. Let's use a set of a material that input CLT. Let's use the same set of material. Let's do this. This is my code. I want to use layer material like this. Let's use this layer materials. All right. This is Pascal. Oops. I'll give you a minute or two. You can set this up in your code. If you already set up this way, let me know. But if you finished, just say done on the screen so I know you're done. Set your lamina property, all of them is 6 layer to this set of materials. All right, let's set thickness to be 0.00, 0.020 then. 0.02, let's see. All right, thickness 0.02. And the angles, let's look at a symmetric laminates, which is 0, 45, minus 45, minus 45, 45, 0. Let's look at the symmetric laminates. All right. Now look at your ABD. This is ABD in my case. Copy this over here. All right. All right, the dominant feature of symmetric laminate is the B matrix is essentially 0. So this matrix is all very small numbers, either pure 0 or almost 0 compared to other terms. This term, the same here. Symmetric laminate B matrix is 0. And your calculation should show the same thing. Okay. So we're talking about the symmetric. All right, so what I want to do now, is everyone done with this? Everyone done with this? All right, Thomas is done. Okay, let's make this anti-symmetric. Let's see what happens. Let's make anti-symmetric is, let's just cook out anti-symmetric. Let's do 45 minus 45, 30. All right, so anti-symmetric means that this will be minus 30. This will be 45. This will be minus 45. See, everything, the midplane is this is what below 3, right? So you see this symmetric location. You compare these two, they're negative. You compare these two, they're opposite. These two is opposite. Okay, let's make anti-symmetric. All right. And this is anti-symmetric. Let me make a new. And then my layup is this, my layup. This is my layup. All right, what else do you see? Other than the B matrix is not 0 this time. B matrix non-zero. What else do you see? And you have A16, A26 equals 0. And these two equal 0. Sorry. D16, D26 equals 0. These two terms and these two terms. These two terms. And these two terms. So you have bending tension coupling, but you don't have a tension shear coupling. You don't have bending twist coupling. Okay, that's anti-symmetric. Okay. All right. You can cook out other type of layout unless, I mean, as long as anti-symmetric, these all apply. This is non-zero, and then you have these terms are 0. All right, and then let's cook out a quasi-isotropic layer. Let's do a quasi-isotropic. All right, so I'm going to do this twice, minus 60, 0, 60, and minus 0, 60, minus 60, minus 0, 60, minus 60, 0, and 60. All right, so this is my layup. It's ABD. Now, these are the characteristic of quasi-isotropic. So basically, A matrix is equivalent to some isotropic material in the sense of extension. Okay. Any questions? Any comments, questions? All right, let's look at some coupling effects. let's cook out a layup and let's apply load and see what is we can apply different kind of load. We can apply tension, we can apply bending, we can apply twist, or let's see how the deformation of plate is. So let's start with a symmetric laminate. I'm gonna cook out a symmetric laminate, which is oh, let's do a cross ply then. Let's do cross ply 0, 90, 0, 0, 90, 0. This is the symmetric laminate cross ply. The reason we call it cross ply is made out of 090s. All right. I'll give you a minute or two. Now, the input your input this into your code. Make this the layup. Symmetric cross ply. All right, let me know when you're done. Set symmetric cross ply. Okay. You can also do the sum up like Noah did. I don't know how you do it, but if you did, give me a sum up if you finish this. Or you can keep doing this. If you haven't done it, I'm just gonna apply load. Let's apply a simple extension load. Let's pull in the n direction. So I'm gonna, in my case, I just apply load here. Let's apply 3E6. This is my load. All right. And then I put this into table form. This is my load. And this is deformation. Now, what do you see in deformation? Deformation is, well, the pronounced deformation is just stretching in the direction we pull. You see the epsilon x0 is the direction, the stretching, the strain, right? That's the most pronounced, the largest among all strains. And then there's a little bit of shrinkage in y direction due to Poisson effect, right? So in the y direction, in plane shrink a little bit. Everything else is 0. You don't have any shear. You don't have any bending. You don't have any twist. Those these terms are essentially all 0. These are 0 terms. So for the symmetric cross ply, no coupling. You pull it, extend. There's Poisson effect. There's no shear, no bending, no twisting. Okay. You see the same thing? Who has done with this case? Okay. All right. Let's look at something with tension, extension, shear coupling. Let's do apply with let's change the apply to angle plies. Angle ply is plus minus theta type. So we're gonna do an angle ply, which basically 090, 0, 45, 30, 30, 45, 0. This is sort of angle ply. Okay. So symmetric angle ply. All right, I'm gonna apply the same load, which is the tension, and then so I'm pulling this in the X direction, and this is my deformation. All right, so this one has tension shear coupling, which is this term. I'll give you a minute to set this up. If you're done, you see similar results, you can either sum up or type something in the text. All right. So angle ply, this is occurring. Now I want to look at what if I bend this angle ply? I want to bend it. And the way you bend it is you apply a moment. I zero out this tension load. I apply a moment. Let's say I got 3E6 here. This is a bending. What happened? This is your you pull in the tension. This is you put in bending, pure bending, no tension, just under bending load. And what is the deformation here? I'm gonna also copy the ABD matrix here so we have record of it. This is the ABD matrix. So this is the case when you have pure tension. This is the case when you have pure bending. So what you see here is that all these terms are essentially zero. So there's no bend tension coupling. I mean, is what predicted for symmetric laminates. Symmetric laminates. The symmetric laminates, BE is 0. Okay. So there's no bend tension coupling. So if you bend it, it doesn't extend. Okay. Which is shown here. These are essential 0. These are very small numbers, close to 0. Okay. But in this case, we have a bend twist coupling. You see, when you bend it here, this thing twisted a little bit. They also bend the other way. This is a little warping. So when you bend in X direction, the Y direction also bend a little bit, and they'll also twist a little bit. This is due to the fact that these terms are not 0. These terms are not 0. That's the cause of it, because these are coupling term. Bend twist coupling is because these two terms are not 0. Now, what do you think if you twist this material? If we twist this material, what will happen to the bending, to the curvature? What would happen if you twist it? Now let's try it. We twist it. This is a so we loaded pure tension. This is the response of the symmetric laminate, and pure bending. Let's do pure torsion. All right, torsion is this term is a torsion term, mxy. So I make this bending 0. I make torsion 3e6. So torsion load. I twist it. I try to twist it. This term is what's applied. And what's the output? This is the output. Oh, you see here, these remain to be 0. These are the extension deformations. And you have a twist for sure. When you apply twist, you have twist. The twist is pretty big. This is a 2.07 is the twist, right? But you also have bending. So when you twist it, this material also develop a curvature in the XY direction. Right. So this is so usually the coupling is reciprocal. So when you have a bending twist coupling, you apply bending, you have a twist. You have a torsion. When you apply torsion, you have a bending. So that's the point here, because these coupling terms. All right. Who has done all these 3 cases? Do you get the same curvature? All right, let's look at the anti-symmetric again. Anti-symmetric laminate again. Let's cook this out. I want to apply some load to the anti-symmetric. I'll go back to this case, anti-symmetric. Let's go to my layup. I'm gonna make this 45 minus 45, 30 minus 30, 45 minus 45. All right, it's anti-symmetric. I want to bend it. So I'm gonna bend it because 3.0 E6. Let's see what happens. This is the load I apply. Pure bending. And this is non-zero. This is an interesting term here. And the output is this. Oops. let's see what happened. I did nothing but bend it. I actually have shear. You see this in-plane deformation? This is strange. So this is due to coupling effect because my B matrix is not 0 now. So I have some big terms, really these big terms. So that produced the bending shear coupling. Shear considered in-plane shear, in-plane deformation. So my out-of-plane bending produced in-plane shear. Now these first two terms are essentially 0. All right. The other interesting is I have no twist. I put a pure bending on it. See, I have a curvature in both directions. It's a saddle shaped. This look at deforming the saddle shaped plate, but no twist. Look at the twist. Twist 0. No twist. So there's no bending twist coupling here. All right, so that's due to the fact that these two terms are 0. Okay. Now let me apply a twist to it. I apply a twist, which will be 3.0 EO. I have 0 moment. I apply a twist. This is a pure torsion. And this is my input conditions. And my output is this. Now this is very interesting now. Now when you twist it, it actually produces in-plane tension in both XY directions. You see? There's no shear. This is 0. But when you twist it, the material actually stretched in both XY direction, in both X direction and Y direction. Right? And there's no bending. You see, these are 0. You only have a torque. So there's no twist bending coupling, but there's a twist extension coupling. Okay. All right. These are basically the important types. What we played with is we played with a symmetric laminate, and we played with anti-symmetric laminate, and we played in also isotropic laminates. You can see the coupling phenomena in composites is pretty rich, and you can tailor them by playing with the layups. And the general types, I think I believe went through all the general types, whatever. So the B matrix is really controlled by whether you have symmetric, unsymmetric, or balanced type. If you're symmetric or balanced type, and then it's 0. And the D term is interesting. D term basically is the what enables the aerolux tailoring of the wings. Is basically also has strong dependence on symmetry. When you have anti-symmetry, D are 0s. Okay. So that's a brief summary. If you're interested, you can play more layups. I think that's what I want to play today. Once you produce these things, I know a lot of people couldn't, due to schedule issue, couldn't sign up for class today. You can play over this weekend. You just try to produce your result similar to what I show here. On a few cut and paste on a few pieces of paper and email to me, just as a record that you've done this. You play with these different layups. You know. So I have a record. I will show you. Finish this. This is a sort of a completion of homework 1. Okay. Yeah, I will upload this video right away. I also upload this PowerPoint, so you have these things. Okay. Any questions? All right. If no more questions, I don't have any other material to go over today. I will. Yeah, you try to email me on Monday. And try to finish and email me on Monday. I believe some of you already finished. It looked like Thomas and Connor did pretty quickly. If you finish today, you just email me just a few results, and that's fine. That's you're done. If you have trouble getting to work, you debug a little bit, and you can try to get it work next few days. Try to finish on Monday. You think that's enough time for you, Michael? Okay, give it a shot.
You just want us to send you the results of the same ones that you had inputted? Just
Yeah, these cases.
Okay.
Okay.
Thank you.
All right. You all have a good weekend. I'll see you guys on Monday.